Okay, well, let's get started with looking at some of the theory behind nuclear magnetic resonance spectroscopy. We've had a little bit of practice at looking at what these spectra look like, but let's start looking at what the science is behind it. This picture here is actually, this is about a 600 megahertz NMR. It's a bit older. What we can see down here is the little towers here, which are the radio frequency, where the radio frequency is set in. And then this is the idea of a spinning nucleus that interacts with B0, which is our magnetic field. But let's start having a look. So we've talked about how there are a lot of different spectroscopic techniques and how they make use of different parts of the electromagnetic spectrum. So basically, we've talked about infrared, ultraviolet. We've also talked about X-ray crystallography is coming up for us for HL. UV-Vis, a number of you used in your IAs, and then of course mass spectrometry we've looked at as well. So this time we're looking at our nuclear magnetic resonance spectroscopy, and this is basically telling us how things are connected, what the signal or the atom that we're looking at that is responsible for the signal can see or interacts with that is close to it. Okay, so essentially what nuclear magnetic resonance spectroscopy works on is the idea that spinning charged particles cause a corresponding magnetic field. This is because some nuclei will have a magnetic moment. We call this a spin-a-half number. We don't need to calculate spin-a-half numbers, but essentially what it is that they can have a spin that is aligned with an external magnetic field, so it will run parallel to that magnetic field, or we can have a spin that is aligned anti-parallel to the magnetic field. These are the two energy states that are possible: the aligned or unaligned, so the aligned or the anti-parallel. NMR really is one of the most powerful techniques that is used by chemists today for determining structure. It can be used for small molecules, proteins, anything like that, and we only look at a very small fraction of what it's able to do. We do need to remember that it is using radio frequency from the electromagnetic spectrum, so we're talking very large wavelengths, low frequency and low energy. So we're in this energy range here, which is lower than infrared. So we're in a very low energy range here, okay? Remembering that also infrared is up here, AAS UV-Vis is in the visible, and then we will look at X-ray as well, and we've looked at gamma rays in HL for radiochemistry. This is just an idea of what some of the machines look like. The one that was on the front page here, this is a larger, this is about 900 megahertz. Again, it's a fairly old machine. As we saw, these are getting quite small now. The technology is improving and we're seeing some miniaturization happening in our technology, meaning that these are getting smaller. But every NMR spectroscoper will have a workstation, which is simply where a computer is, an NMR console, which is where this is where your monitor is, this is where your actual computer is, a panel here which tunes in the frequency which goes into the probe. Then the probe goes up through the machine and the sample sits down in here, and this is our magnet that sits on either side of it. Okay, so we have a detector, we have a powerful magnetic field, we have a radio signal that is pulsed into our sample, and our sample that sits inside the magnetic field. So the radio transmitter, this is how we dial up the frequency and how we select what nucleus we're going to look at, be it proton or carbon. The magnet, which produces the magnetic fields that we're interacting with, and a sample, and then a receiver, which is basically how we detect the signals. So essentially the most common form of NMR is Proton Nmr, and we've looked at Proton Nmr a lot. This looks at the hydrogens in a molecule, okay, and it gives us information about the structure of the molecule that contains hydrogens, which is pretty much any hydrocarbon that we can think of. So there's a number of different molecules that we can look at. Pretty much all these families here will give us different information by the hydrogens that are present on them. So we can see here that we have different hydrogen environments, different types of hydrogen, we can tell those apart. Okay, so if we have a spinning charged particle, which is our nucleus, okay, so essentially certain nuclei act like little magnets, and this is because they have uneven nuclear spins. Okay, so protons, neutrons, and electrons can have all spin on their axes, and they either have an up or a down direction. When these spins don't balance each other out, then we end up with, because the nucleus is spinning overall, it doesn't balance out, the nucleus spins overall. That spinning of the nucleus gives it a corresponding magnetic field, and it acts like a little bar magnet now, so that when we place it into a magnetic field, it will interact with it. So if we have no external field, the little bar magnets that are atoms will basically align randomly. But as soon as we put in a magnetic field, they can align with the field or against the field. So with the field is a lower energy, against the field is a higher energy. Okay, so with the field, low energy, against the field, high energy. And it's these two energy states that we're going to change between. So essentially, this parallel alignment, which is aligned with the field, okay, and then anti-parallel when it is against the field. This is just different terminology that's used from time to time, but it essentially is the same thing, that idea of a low energy state and a high energy state. So when the radio waves are placed in, they are of equal energy that causes this transition to happen, and we can measure the absorption of those radio waves. So as I said before, our nuclei are randomly, before a magnetic field is applied, they're random, interacting with each other. The spins are just in any direction. When we apply these magnetic field to this, we get this idea where the majority of them will align with the magnetic field. There is always some molecules that might have, or atoms that will have a slightly higher energy that might be against the field, but the majority of them are going to align with the field, like fish swimming downstream. Okay, they're low energy, they're going with the flow, and they're heading that way. So when we put energy in, we can cause a spin flip. So this is our little guy that was aligned with the field. If we add in energy, okay, in this case radio energy of a particular frequency, then it will jump up and have the higher energy state, which is a spin flip. It will flip its spin to an anti-parallel orientation and then relaxes over time, and as it relaxes it emits this energy again. And as with many of the spectroscopies, it's this emission that we are measuring when the radio waves are re-emitted. So not every nuclei is magnetically active. Okay, so they have to have an uneven number of nucleons. Okay, so proton will always have an overall spin because it only has one nucleon, so it will always be magnetically active. But the other one that we look at is carbon-13. Carbon-13, okay, is the isotope of carbon. It only has a low abundance, so there's not as much of it, so it takes us longer to get a signal, but it is magnetically active. There are others, but we don't tend to look at them within the scope of the course. So you can imagine nitrogen-15, phosphorus-37, those kinds of ones can be detected using an NMR. They have limited application, remembering that most of the molecules that we want to look at have carbon and a hydrogen, so we can get the information that we want. I suggest you pause here and have a look at this video on the intro to NMR, or look at it after this, but this will give you a little bit more of a brief introduction. Okay, so as we said before, the way spectroscopy works is the difference in energy gives rise to different signals. So the detector will detect the different energy signatures and then give us different signals. These signals can tell us the identity of the nucleus. Okay, so we'll get a different spectrum from hydrogen than we will for carbon, and we can only probe one type of nucleus at a time. So we don't get a spectrum that has carbon and hydrogen on it. But it can also tell us the chemical environment surrounding that nucleus, so what else it is attached to. So, if we think about the fact that electrons around each nucleus are also spinning, they'll have a magnetic field, and the interaction between that magnetic field and the applied one, so the one from the machine, can shield the nucleus from that. So it can protect the nucleus from interacting with that. We call that shielding. So the amount of shielding depends on the number of atoms and type of atoms around the nucleus, and therefore determines where it turns up on our x-axis. Okay, so it changes the energy required for a spin flip to occur if you think there is this kind of buffer zone done by the electrons that's protecting the nucleus from being interacting with that energy. So the energy required to make the flip happen, okay, is measured in chemical shift, and it's given the axis label of delta ppm. You don't need to know what it means. It relates to the magnet strength and a few other things. There's a formula for what it stands for. We don't do that within this course. We just need to know that it's chemical shift, and we refer to the values in the chemical shift as delta ppm. So what shielding or deshielding means is that in a perfectly alkyl hydrocarbon, okay, so a normal chain, protons will behave in a particular way, and we can record their chemical shift. But that chemical shift can change depending on the environment that the nucleus is that we're looking at, in this case hydrogen. Okay, so a CH2 will be slightly different to a CH3 because of the connectivity and the way things are. These hydrogens will have a different energy than what perhaps a CH3 will. And then again, if we add a hydrogen to electronegative element such as oxygen, we see a big shift because the oxygen draws the electron density away, making this proton more exposed to interacting with the radio wave, so it changes the energy level that we see that occurring at. Okay, so that's basically it for all the theory. The rest of it is on how to interpret and work out our chemical shifts, and we'll look at that in our next videos.